Welcome again, everyone. So, the last time we described the classical paradigm of physics and we laid out some experimental results that made it clear why we could no longer proceed with the classical paradigm of physics and it needed some modification, specifically quantum mechanics. And what we did after the experimental results, the double slit experiment, we saw that we had a wave that we had to derive some sort of equation for because when we have a wave that determines physically observable quantities that we can measure, we need an equation that can actually determine it quantitatively. So we derived the Schrodinger equation. So this lecture, I'd like to actually solve the Schrodinger equation for you and run through a problem, particle in a box. It's the standard problem we solve. To show you how we actually solve problems with and get these wave functions for real physical systems. So with that, let's solve the Schrodinger equation. Let's write it out first. Last lecture, I dropped this term here. I'm used to working in natural units. So we have this wave function here. And I'm not sure, I don't think I physically interpreted this wave function for you yet. Um, you know what? I'll do it after I solve the equation for you. So what we did is we derived the Schrodinger equation here. And the Schrodinger equation, when solved, will give us this wave function psi of x here. And this wave function psi of x will essentially be all the information we have about our quantum state equals, notice we're bringing complex numbers here now. The time partial. This is these notation I assume you're familiar with. These are partial derivatives. This is the partial derivative over space of how this quantum wave function changes over space. Second derivative. And this is the partial derivative of how this quantum wave function changes over time, right? So this is Schrodinger's equation. It's a second order equation because of this. It's linear. That's extremely important in quantum mechanics because we're going to be making a lot of linear superpositions, and linear superpositions is going to be really like very, very important in pretty much everything we do in quantum mechanics. And it is a partial differential equation because it's relating how this wave function changes over two different variables, not just one. So how do we solve this guy? Well, when we're dealing with partial differential equations, the first thing we usually do is something called separation of variables. And that the first step in that is assuming that we have a solution of the form this. We assume that we can kind of get a solution that can be decomposed into a product of just space. Oh, I'm so sorry. This is a function of space and time. Right. So we're assuming that this guy, this psi, can be decomposed into a function of space and time. And I'll call this x of x and psi of t. So what we're assuming here is that this is actually just a product of these two things, right? This is an assumption. It doesn't have to be true, and it isn't true in general of partial differential equations. This is the first line of offense, basically, that we use on partial differential equations. Doesn't always work. Happily, it will work in this situation. We're going to prove that for you now. Okay, so we have our Schrodinger equation. We're just going to kind of plug this hypothetical form in here for you. X of x squared of t. Right. Um, and because this is a partial derivative, you're probably already seeing where we're going with this, which is that it's not going to affect this. This is partial x. So the definition of a partial derivative is that it really only acts on the variable that it's interested in, which is the space derivative. So this is not going to be affected by that. It's basically just going to be, as far as this is concerned, this is just a constant function. It's just not going to touch it at all, right? And same here on this side. We're going to have It's not really going to affect that. Right, right. So, yeah. So we're just going to kind of have this like hanging outside this derivative here. Um, this is going to be concerned in the derivative. So we're actually going to get this now. The derivative is only going to be, the partial derivative is only going to be acting on this by definition of a partial derivative. That's just what it does. And this is just going to kind of be hanging out outside here. The partial derivative doesn't act on it in any way. This is unchanged. Okay, and now we're going to divide through by this whole thing. Sorry, bear with me through the math here. Maybe this isn't so interesting to some folks, but for a theorist like me, I like to derive everything. I like to know where everything comes from. Otherwise, it just bothers me emotionally. Now it's 1 over x of x plus p of x. That totally goes out. That and and now that's 1 over this. Okay, this is looking good. Why is it looking good? Well, it's looking really good because this side now is only a function of x. This side is only a function of x, and this side is only a function of. Oh, sorry, you can't really see that very well. Whoops, there you go. Yeah, see, sorry about that. Not really. Right, so this side is only a function of t, right? Let me just. Better? Better. Okay, so this side, yeah, this side is only a function of t, and this side is only a function of x. So this is interesting. What this actually means is that this should only be, when we change x, this should not change because it's only a function of t. And when we change t, this should not change, the left-hand side, because it's only a function of x. Yet they're equal to each other, so we kind of run into a problem here. Because if I change x, if I decrease x and this increases, this has to increase too, because they're equal to each other. But I just told you that this is independent of x, so we've run into sort of a contradiction here. There's only one way out of this contradiction, which is that these both have to be equal to a constant. They both have to be constant. They can't change when we vary this. So what that's actually going to give us is two separate equations here. The left-hand side is going to be equated to a constant, and it's going to be called the time-independent Schrodinger equation, which is going to be this. And this is what we're going to be solving to give us psi of x, which is kind of just the spatial equation, the spatial wave function, which is going to essentially tell us if we have like a particle and we solve it for this particle, it's going to tell us the probability of where this particle is in space. That's all. So in general, the solution to this guy depends on the potential energy of the problem, which is problem dependent. Whatever the potential energy is in the problem, it could be a free particle, it could be in a gravitational potential, depends on the problem, and the solution depends on that, right? Of course, that's just physics. Same with F equals ma and all that kind of stuff. Any kind of physics will depend on this term right here, right? X equals, because what are we doing here? We're multiplying it through, right? We're equating this to a constant. Perhaps I skipped a step. I have. Okay, so I'm equating this left-hand side to a constant here, and I'm multiplying it through by psi of x. So psi of x disappears here, it gets multiplied by this, and then it gets multiplied by this, right? That's all. And this is just the name of a constant. I'm calling it E because it's going to turn out to be the energy, because it turns out that this whole thing here on this left-hand side, um, it operates on this, which, as I believe we discussed in the notes, it's a vector. And this whole thing, this differential operator here, is, in fact, you can represent it as a matrix. It is in the Heisenberg picture. It's called the Hamiltonian. It's the energy operator. Its eigenstates are, its eigenvalues, rather, are the energies of the system. So what this is actually kind of saying is that the full Schrodinger equation, what it's actually saying is that the Hamiltonian operator operating on the wave function actually evolves the wave function in time. That's what it's saying. Save for these constants here. That's why I was dropping the constants, because this is the real important philosophical statement of the Schrodinger equation. So this is the left-hand side, the time independent side of the Schrodinger, equation. The right-hand side we can actually just solve. We set this equal to a constant as well. It will also be equal to energy. So we have this I h bar dependent. Sorry, it's sun's in my eyes. Well, the psi thing here changes in time. And it picks up this thing here over h, right? But set it to a constant. But of course, we're just going to multiply this by the constant. And what we've done here is we've solved the partial differential equation by reducing it to an ordinary differential equation, an ODE. And we know the solution to this. We know it and love it. It's, of course, just a regular exponential, but because of this, it's not going to be a regular exponential. It'll actually be sinusoidal, technically. So we're just going to have this be equal to this, because what this is saying is the way that this changes in time, the partial derivative with respect to time of this function is the function again itself times this constant, e over it, or ih, right? And we are going to have to do this because you don't want that down there. Just multiply both sides. That's how you have to do that with I. Right? I'm assuming this is familiar. People are familiar with this. So this is just going to be equal to this. No, just one I, please. Over h bar, right? Radio. Now, to get the full solution, remember we assume that this is equal to, what did I call it? X of x times this guy, right? So we just multiply these by each other. X of x, and this is just, again, fully solved here. E negative I over h bar, right? So this is actually generally the solution, and this part is how it evolves in time. So if you leave a quantum state alone, if you leave a quantum state alone and unobserved for a period of time, that's how it's going to evolve and change. How the wave is going to squiggle out or squiggle in or whatever the heck it's going to do. That's the time evolution part. And this part, again, in general, depends on the potential of the problem. So we're actually, yeah, you know what? Let's do particle in a box here. So now that we have solved the Schrodinger equation, let's show an application of how we actually do this now. Okay. Particle in a box, what is it? We got well, or potential. It doesn't matter, because potential, you can do whatever you like with it. This could be any potential. You can add a constant to it. But essentially, this could be, the idea is there's a hard wall here. The particle can't go beyond, because the potential is infinite. So the particle can't really go out here. And in here, there's a finite potential, but this is what I was saying before, you can add a constant. So we might as well just say it's 0. And again, there's a boundary here. So this is x equals 0, and this is x equals L. X equals L. Right. So now that we have our potential configuration, we can solve the space part of the Schrodinger equation, and then we just append this part. Right. All right, let's do it. So we don't have a potential. Potential is 0. So we just have this part of the equation. Negative h bar over, yep, squared over that, over that, over that, over that. Right, and we're just doing that. Plus 0 equals, again, energy times this, this, and this, blah, blah, blah. And, yeah, so we know what this is. This negative is going to come over here. So, again, this has been reduced to an ODE. And we know the solution is a sinusoid, right? Because it's a negative. So you take the derivative twice, and you get out the function again, but it's a negative. What function does that? We all know it and love it. It's a sinusoid. So we're going to be getting the general sinusoidal picture is going to be just an A cosine plus B sine, right? So that's the solution to that. In particular, it's going to be of kx, this argument here. And that's going to take the form of E over h bar E2m. Okay. We're going to use these boundary conditions to determine k here, actually. So the first boundary condition is whatever kind of wave we have in here, it has to be 0 here, and it has to be 0 there. It can't exist here because there's an infinite potential here. This is just kind of the way that we've rigged up the problem. We don't want it to exist out here. We don't want it to exist out there. I'll say a little word about why we have to do that later. Essentially, we'll have a much more complicated problem if we allow it to happen. But suffice it to say, for now, those are the parameters of the problem. So we actually write that down mathematically by saying this. Psi of x, or x equals 0, equals 0. So in that case, this thing, when x is 0, needs to equal 0. A of cosine of 0 plus sine of 0 is 0, right? Plus 0. So 0 equals A. A needs to equal 0. Okay, so this goes out, and we're dealing with a sine. Let's apply the second boundary condition. Psi of L needs to equal 0. Okay, so this is going to determine this. B of sine KL needs to equal 0 now, right? What that actually means is that KL needs to equal n pi, because we need this to be 0. And sine likes to be 0 at 0, and also at 180 degrees after that, which is just n pi, right? So as long as this argument is n pi, then we're going to get a 0, and this condition will be satisfied, and this wave will disappear here. That's what we need. So what that actually means is that k needs to equal n pi over L. Good. Very nice. So now we have a nice little wave function here. Sine n pi x over L. That's the wave function. But there's a little bit of an issue with it, which is that when you're dealing with probabilities, remember this wave function, what it physically represents is the probabilities of a particle or whatever being at different positions. So the particle has to be somewhere. So if we add up the probabilities of it being in every single possible position, we better get 1 because we're dealing with probabilities. So this stage is the iconic normalization of the wave function. So we're dealing with a continuous variable here, x. So we're going to be using an integral rather than a sum here. So we're going to do some integration here. We have to integrate the wave function. And what we actually want specifically is the x. We want all the probabilities to add up to 1, right? So we want sine squared and pi x over L dx b squared to be equal to 1. That's the normalization condition. Believe you're actually equal to cosine 2n pi x over L plus 1/2, let's say. Is that right? Maybe it is. Let's hope so. And then we integrate this guy to obtain sine. I believe something comes out here. I believe just the argument comes out here, right? Yeah. 2n. No. Sine 2. It's been quite a while. What's it over to? And oh, I'm sorry. That's very important. Boundary conditions. Between 0 and L, right? Between 0 and L. So what we're looking for is the area under this curve between 0 and L. That's going to be the total probability. And again, this probability had better add up to 1, or we're not actually finding probabilities. We don't have a physically real state. Yeah, between 0 and L, right? L, dun, dun, 0, 0, 0. Okay, so this whole thing goes out. Yeah. Okay, yeah. Okay, I did this right. Thank God. So, sorry. So, L over 2 minus 0. Yeah, so it's L over 2, right? Yes. L over 2 equals b squared. So our normalization factor is going to be square root of 2 over L, I believe. So our fully normalized wave function is going to look like this. Square root of 2 over L, where L is the length of this well. Sine n pi x over L. Yeah, that's the wave function, right? So it's not gonna look like that. What will it actually look like? Well, we have this Chekhov's n here. And what that represents is actually the different energy levels of the system. These discrete energy levels that we referenced before. Now, energy is quantized, as we said before when we referenced Einstein's photovoltaic experiment. We can actually just show energy is quantized with this as well. In particular, I'm trying to remember how we do this. In particular, yeah, let's just graph the wave functions. I don't want to get into energy quantization right now. The first one's gonna look like this because n equals 1. That's just kind of what this looks like. For n equals 1, the wave function will look like this. So we can talk about these are energy eigenstates because I've solved the Schrodinger equation, but I really want to just concentrate on the position wave function because we're talking about eigenstates of x. These are technically eigenstates of energy as well, so we can actually get an energy eigenstate. But I want to talk about one more thing, so let's just concentrate on the position because I don't really want to confuse you, because these are technically eigenstates of energy and position, but that because the Schrodinger equation is the solutions to the Schrodinger equation are eigenstates of energy. But I really just want to concentrate on the fact that we're looking at eigenstates of position right now. So think about this as where the particle is position-wise, x-axis, right? For N2, we're going to look more like this. Pick up a node. And again, this is squared for the probability, so it looks like that. That's the probability for n equals 2. So this is our first wave function that we've actually solved, and it's going to tell us where the particle is, where the probability is, right? It's probably here. It's definitely not at this node. This looks more kind of like a normal function. It's just one lobe there. So yeah, this is our first wave function that we've kind of solved here, and it kind of tells us where the particle is going to be in space in this probability distribution that we referenced before. So yeah, pretty cool, right? Now, when we get to quantum computing, just a kind of little segue here, we're not going to be worrying about this continuous variable. What we actually are going to be doing is remember in lecture 1 when I talked about the particle, the classical particle as system. This is the quantum particle. And remember what I did with the classical particle is I restricted it down. I restricted the physical state space from this x here of like infinite continuous variables down to just 2 variables, 1 and 0. And then I made memory out of that. That's kind of what I want to do now in a quantum sense. We have this quantum particle now, and it takes continuous variables over all of space. Now I want to restrict this down to what's known as a qubit. And that's kind of the quantum analog of what I did before. So instead of taking all possible values over all space, the state space is actually just going to be a classical 0 and a classical 1 now. So that's what we're going to be doing in the next lecture. All right, cheers.